Okay, this is our fifth example of an equilibrium constant type problem that requires an ice table. You can see from the number of examples that you really should drill quite a few of these since there's a lot of different scenarios that can crop up. Let's read the problem and see what's going to happen. The equilibrium constant, which is extremely low for the synthesis of nitrogen monoxide, is given at 1500 Kelvin. Note we'll ignore that since it's holding steady. The initial concentration they give you is 0.8 and 0.2. Those don't fit into the equilibrium constant expression but are used to solve for it. We'll find the concentrations of the reactants and the products when the system reaches equilibrium. So you're seeing a lot of times where they just say, what are the concentrations of everything in the flask once it's done, quote unquote, meaning hit equilibrium. And for that, those are usually the harder kind. You have to express each of the three concentration in terms of a stoichiometric ratio. None of them is particularly satisfying because they say plus x, plus 2x, 0.8 minus x, that kind of thing. But it can be solved. So let's go ahead and take a look at it. I know from advance that for a lot of these problems, when they say give the concentrations, you're going to be making a big thing called a quadratic assumption. And for that, trust me for now, it's handy to see if what quote unquote 100K is less than A. Notice that K is very, very small. They really have to set it up that way if they're going to be able to make the assumption we need to make. Once you see how this thing sets up, you'll see that it's a little bit ugly. So let's just see if it's going to require a quadratic solution. This might seem like, why is he doing this? But once it's done, I think it'll make sense. 100K is still in the value of 10 to the minus third, and A means the concentration of the lesser of your reactants, which is 0.2 molar here. And 100 times this is still in the 10 to the minus third value, whereas 0.2 is a lot bigger than, for example, 0.002. So yes, we will be able to make that assumption. Let's see why that kicks in. All right, the way to solve these is to set up your equilibrium constant expression. So it's going to be equal to products over reactants, so nothing gets omitted. See, it's all in the gas phase. It'll be the concentration nitrogen monoxide squared divided by the concentration of each of these. And since each of these are going to go down by a little bit, we'll call that x. So this will be 0.8 minus x. This will be 0.2 minus x. And this will be plus 2x, right? It'll be twice as many, two of these form for every one of those that go away, so we can say plus 2x. We know that outside the parentheses, it will be squared since we have the 2 there, giving us something that looks like this. But notice I didn't say 0.80 minus x and 0.20 minus x because of what we call the quadratic assumption. If we had those there, if they were the same thing, it would have been quantity squared and we're good, like we showed in another problem, but they're different. And so solving this is what they call a quadratic problem. But since the x is really, really small, we're going to omit it from here and here, which I did directly. We can now solve for x, which I'll show stepwise in a minute, but it ends up being that value. That's not the answer, but it's 2/3 the answer is already there. That's the concentration of each of the reactants. The concentration of the product is 2 times x. It's not squared. That's just used to calculate Kc. That's the actual concentration of that stuff in solution. So it's going to be double that, which is like 1.2-ish, 1.26 times 10 to the third. Did I get that right? Well, it doesn't matter. It's going, 1.3 times 10 to the third. We did we used 2 significant figures in our answer. And those are the 3 answers to the problem. I believe that should be in square brackets. Okay, let's show the ice table method. This simply points out that we always ignore temperature for these problems as long as it's constant. It needs to be constant. They always have to show the temperature. We can always ignore it as long as it's constant. Write down the same K type situation, the same equilibrium constant expression. But in this case, that's what they're given, the initial conditions. What's the change? This goes up double what the other ones go down, just by virtue of the 1-to-1-2 stoichiometry. And so we just take each column and add it up. And there you go. Notice that we go right here. That's what we call our quadratic approximation. And now we're at the exact same stage. And there they are. Now, solving for x. we can say this. I would put 4x squared right there. 2x quantity squared is 4x squared. We're going to cross multiply. 1.6 times 10 to the minus 6. That's this times that equals 4x squared. X would equal x squared would equal this divided by 4. X would equal the square root of this divided by 4. And there it is, 6.3 times 10 to the minus 4th. It's a match. Now you could skip this final second ice table. My God, these get too time consuming, and I would really recommend you do on an AP exam. I would simply say that's the value of x. I already knew the concentration of the two reactants. Twice that is simply the concentration of the products. And so it's going to be 1.3 times 10 to the minus 3rd. But there it is. If you draw another ice table saying that's point, there is x, x, x. See how it's minus x, minus x. I'm just plugging in for x plus 2x, and you can do it this way. Do you need to? If you want to, do it that way. It's the slower way. The more you can do in your head, the better. You might say, oh, I'm going to do the ice tables for now. Once I get really good at it, I'm going to try to skip them sometimes. Or, I got tons of time on this test. I'm just going to do the ice tables all the time. It's your choice. But this is, I believe, our 5th example of an equilibrium problem that uses an ice table.